Okay, let's get started. So we are happy to have Yutin Huang from Taiwan. He's going to tell us about the silence of binary Kerr.
Okay, thank you very much for the invitation, and I'm really excited to have this opportunity to discuss this recent work of ours, which was done in collaboration with Rafael Daoudi, Ming Zicheng, who is my PhD student, Camila Mercado. Both of these are postdocs, and Man Quan Tan, also my master students. And even though this is a more recent work, but it's really based heavily on works that has been done in the past around 1 or 2 years, along with which includes collaboration with Nima, Zizhen Huang, also my previous student, Junwoo Kim, a PhD student who just an excellent PhD student who just graduated. He's going to Queen Mary, and of course Simon Lee, who's actually in the audience. So this talk will be basically 2 parts. So the first part will be more or less like an overview of work that is done here, which was what motivated us to look into this issue about entanglement in spin space. So I would like to have like a more motivation and discussion about how we went on to looking at these properties. So I'll probably have the time discussing about works that are done in the past year and discuss how it led us to this question. So let's begin. So basically, we can start by talking about the no-hair theorems, which is basically that we usually say that black hole is characterized by the mass, charge, and its spin. And these are the only quantum numbers that you need to characterize a black hole. And you'll notice that these are exactly the same quantum numbers that you would use to classify an elementary particle. So then it's natural then to ask, in which sense can you describe black hole as? Is there a certain regime where you can discuss about dynamics of black holes and by treating it as a particle? Now, of course, there's a lot of, if you think along this way, then you realize that there's a lot of already work done in these aspects, and that's actually in the computation of the gravitational wave coming from the gravitational merger, and in particular in the in-spiral stage where the 2 black holes or black hole neutron stars are far apart. Basically, usually people treat it as a point particle approximate. So this is nothing new. However, you might say that, oh, but if this is the point of view that one wants to take, then is everything looks like a point particle far away. So what's the big deal? And if you think a little bit more, then you realize that that's actually not the case. So when you're talking about a point particle, so let's begin by looking at how we describe the 2 black holes in this in-spiral stage. And so you want to describe it as a point particle. So when you try to do that, you try to write down the world line action. Now, usually when we talk about world line action, we think about a leading kinetic piece. But since these are background sourcing objects, so that means that we need to add additional, let me use quote unquote, higher dimension operators that along in the world line action. And for example, these 2, if it's just a scalar, if we don't talk about spin degrees of freedom, then these are the leading operators you would write down. I'm using conventions used by the usual GR community, where E is the electric part of the Riemann tensor and B is the magnetic part of the Riemann tensor. So these will be the 2 leading pieces of the effective action of the operator that you can write down. And so for neutron stars, you can compute what these Wilson coefficients are. And it turns out that for black holes, these Wilson coefficients are actually 0 to the best of our knowledge in 4 dimensions. So do you see that there's a difference between black holes and neutron stars, even if you're treating it as a world line theory. And in fact, this is related. This is a very important number. This is what is called a tidal Love number, which basically describes how the object actually gets stretched in the gravitational background. Now, if we actually start thinking about spins, then the story becomes much more richer. So when we're talking about a world line action, when we talk and we include spin, that means that you need to include what spin degrees of freedom, which we usually include here, which is an extra spin field. And once you do that, the possible higher dimension operators that you can write down are infinite. And so here, this is a nice compact form. And this is actually just a leading order higher dimension operators. A leading order in the sense that these are spin degrees of the freedom coupled to a linear Riemann tensor. So there's only one factor of the Riemann tensor here. Okay, so you see that the way that how the objects, the spin couples to the background Riemann tensor actually describes what that object is. So there's an infinite number of Wilson coefficients here that characterize the object, even at linear order. Now, how do we get these Wilson coefficients? So let's say if you have a solution, so for a given solution, basically we can deduce these Wilson coefficients by first we consider the linearized metric. So for example, if we take the Kerr metric and take the linearized form, which we write it in this form, by linearized, I mean that in linear order in G Newton. So this is the first order. And once you have the linearized metric, then you can construct what is called, or what you can think of as the effective stress tensor that sources this metric. And you can, so if you have the linearized metric, then you can solve for what that stress tensor looks like. And then once you have the stress tensor, then you know that in the interaction part of your world line action, then you will have this effective stress tensor coupled to to couple linearly. And so since you can solve this, you can solve the stress tensor from your metric, then you know what these Wilson coefficients are. And so this procedure has been carried out by a very good paper, beautiful paper by Justin Vines. And so in this kind of normalization, you'll find that all the when you're doing this, so when you're matching it to this Kerr black hole solution, then all of the Wilson coefficients are set to 1. So if I talk about a world line action, so if I talk about a world line action, then when these C's become 1, that tells you that this object that you're talking about, even though you're far away, you don't see it, you don't know anything about horizon or anything, but when these C's are set, when you find that these C's are set to 1, that means we're talking about a black hole.
Oh, sorry. Can I ask a question? Sorry, I thought that if I'm far away, then the metric would look, as you were just saying, if I were far away, then the metric, I suppose, if there's no spin, then it looks like threshold. If there's some spin, if I'm sufficiently far away, it would still look like Kerr, right? So I didn't exactly get, if I have a point of some spinning particle, why do I get different C's?
Okay, so yeah, so in the sense that you can come back to here. So of course, by far away, I mean, what I really mean is that we're not really far in the sense that, so for example, in a binary black hole, you're not really asymptotically infinity far away. And furthermore, so for example, here, when you construct the stress tensor from the Kerr metric, you construct, this was sourced the metric coming from Kerr. But if you have a neutron star, then you know that the stress tensor, you also need to include the matter stress tensor. And so that, from that, you will deduce that these Wilson coefficients will be different. So one of the things that people like to work is, for example, for these neutron stars. So of course, for neutron stars, if you want to compute theoretically what these Wilson coefficients are, for example, if you want to compute what these love numbers are, then it depends on the equation of state, which tells you how you should write your matter stress tensor. But yeah, the stress tensor will be different, and therefore these Wilson coefficients will be different.
I see.
Okay, great. So we see that by using these different Wilson coefficients, we can parameterize different kind of spinning bodies. So this is a straightforward thing that one can do, and once one have these actions, then you can take this what is called a one particle effective action, and start to compute the interacting potential and so on and so forth. And however, so what we would like to ask is, instead of as many of you heard and probably know, that when we're talking from an amplitude or from the S matrix point of view, we would really like to not talk about action and talk about observables. So we would like to ask, what is the corresponding on-shell statement of the no-hair theorem, or more precisely, what is the on-shell statement that selects these C's to be 1? So what is special about 1? Why is it not 1.001, or I mean, what is so special about C equals to 1 from the on-shell state, from an on-shell point of view? And furthermore, we also know that there's really a lot of different kind of black hole-like solutions. And even in 4 dimensions, we know that there's, of course, there's Kerr-Newman, and there's even Taub-Knot. So there's all these different kinds of black hole-like solutions. And so if we have an on-shell way of saying what a black hole solution looks like, then how, through this on-shell way, can we characterize the different black hole solutions? And also the third question is that whether or not there's actually some new, from the on-shell point of view, whether there's some new underlying physical principle that actually selects these solutions or select these on-shell interactions that tell us those are simple. And so these are the 3 questions that are in the back of our mind when we really started to think about this. And so we're going to try to answer these questions, and basically, so this talk will be answering these 3 questions. And since I'm talking about on-shell observables, and so I would like to transition from this Lagrangian or action point of view to an observable, the scattering amplitude. So since in the Lagrangian, basically you have this infinite number of higher order interactions. So, and these are viewed as operators acting on physical state. So we can amplitudes by taking these operators, and then we sandwich it between polarization vectors, and then we get basically an amplitude. So for example, for each of these, the reason that you get a 3-point amplitude is, for example, for each of these operators, you have spin operators that acts on the physical states, and then it's coupling to a linearized Riemann tensor. So you know that from this, you can translate into something that looks like this, which is these represent some particle that carries spin, and some particle that carries spins, and this couple linearly to a graviton. So this is basically, so you would expect that each of these interactions translate to some structure inside the possible 3-point amplitude. So we're going to directly look at what are the possible 3-point amplitude by considering this from the point of view of kinematics. So since most of the people in the audience are probably not familiar with the spinor helicity that are used heavily in scattering amplitude, so I will give a lightning introduction. But it's also a somewhat new formalism in the sense that these are massive spinor helicity that covariantize the little group representation. So, which was a paper that we did with Nima and Zizhen back in 2017. Okay, so basically we're talking about, if we're talking about a scattering amplitude, we're talking about transition between an in state and an out state. And so since we're transitioning between states, these states carry quantum numbers. And when we're usually talking about scattering amplitudes, the associated quantum numbers are basically the little group quantum numbers. So since we're talking about 4-dimension scattering, and these are generically massive states, the 4-dimension massive little group is SO3, which use the covering group is SU2. And therefore each state is characterized by some SU2 representation. And the irreducible of SU2 are basically, you can think of it as for spin S representations, we all know there's 2S plus 1 degrees of freedom. So it's basically just 2S of these SU2 indices totally symmetrized. So we know that an amplitude, when you're talking about this transition probability, the amplitude will carry these 2S symmetrized indices for each asymptotic state. So we would like to find objects that carry these indices, and we would like to define these objects kinematically. So we will use spinor helicity formalism, which is basically that instead of talking about a 4-vector, we put our 4-vector into the bispinor form, which is basically take the 4-vector and contract with the sigma matrices. And so then you get a 2x2 matrix that looks like this, for example, in some particular basis. And so p square becomes the determinant. So if it's massive, then it's just saying that the determinant of this 2 by 2 matrix is m squared. And so this 2 by 2 matrix has rank 2, which means that it can be spanned by 2 eigenvectors. And so it's nicely organized in this form. So there's two vectors, two component vectors. And so I can label them as 1 and 2, representing they form an SU2 doublet. And so you can let these SU2 indices contract with each other so that you see that this is SU2 invariance, and which it must, because that's the definition of little group. The little group is the group transformation, which leaves the momentum invariant. Okay, so this is a very important object that we'll use to parameterize our amplitude. So remember that I said that our amplitude should carry these SU2 symmetrized indices. So somebody has to carry these indices. When you're doing quantum field theory, usually the object that is carrying these indices are the polarization tensors or polarization vectors or external line factors, whichever name that you like to use. But those are basically their goal or their role is to carry the non-trivial little group indices. But instead of introducing these objects, here we would like just to use things that are defined kinematically. So we have this bispinner here, the spinner here, we already carry these SU2 indices. So since you know that your amplitude is going to be proportional to these spinner factors, simply because that you need somebody has to carry these indices. So just from the get-go, you know that your scattering amplitude will be proportional to these massive spinner objects. Now, in some sense, you can say that these spinner objects are the spinner representations, or the spinner vector, or polarization tensors. But anyway, so these are, the fact that they're proportional to these things are just given. So the only thing that is non-trivial is that since they form irreducible representation of SU2, so that means these I1, I2 to I2S are all symmetrized. That reflects in that what the remaining factor here is, that here they have to carry the SL2C indices, the space-time indices that are totally symmetrized. Sorry. Okay, so once we factor out the little group carrying factors, then we know that, for example, if we want to talk about the most general 3-point scattering process involving some 2s to 2s massive particle with some massless particle going out, then this object, the tensor structure of this object has to take this form. This is the part where you already strip off the SU2 pieces. So this is a 2s SL2C symmetrized tensor times another 2s SL2C symmetrized tensor. So when we ask what is the possible structures that you can have when you're discussing a spin S, the interaction of a spin S particle with the massless field, then we have to construct what is the independent, we have to construct the basis and to see what are the number of independent bases that can span the structure. And so this is basically what we'll do. So we'll try to, we know that this is our task. We need to span the basis of a 2s times 2s tensor. Now, since each of these indices has SL2C indices, which are 2 components, so you just need 2 vectors to span this basis. So the natural vector, once again, everything we use here, we don't introduce anything new or any auxiliary things. So everything we use is always just defined kinematically. So we already, in the previous year, we already strip off the massive spinners. So the only thing that is left that can span the space is the massless spin associated with this leg. So for example, we can have lambda 3 alpha, which is the massive spinner associated with this leg. And then we can use the epsilon tensor to construct the orthogonal vector, the lambda, which I'll call U and V. So these are 2 vectors. And so basically you can use these 2 vectors to try to span this space. However, things are not that simple. And the reason is because kinematically, when these 2 are the same particle or the same particle of the same mass, the kinematic becomes degenerate. What I mean is that if you take P2 dot P3, for example, you'll see that P2 dot P3 is actually 0. But if you actually write it out, this P3 involves 2 spinners, lambda 3 and lambda tilde 3. And that tells, and the fact that this is 0 tells you that the lambda 3 has to be proportional to lambda tilde 3. And so this is just this is, if you go through a little bit by yourself, you will see that this is trivial. But the reason I bring this up is just that I want to define this proportionality factor X. And it turns out, just to jump ahead of myself, X is actually what describes a black hole. And we'll see in very shortly how that comes about. But the important thing is that this X will play a very important role in this entire talk. So, but the origin of X is really mundane. It was just a very simple fact that it's coming from the kinematics, which tells you that lambda 3 is proportional to lambda tilde 3. Okay, so that means that the 3-point amplitude that we want to construct, there's only 3 building blocks that we can construct, that we can use to construct it. We have this X factor, which actually carries non-trivial little group weight for the massless leg. We have this lambda 3 here, and then we have the epsilon tensor. But that's it. So you only have these 3 objects to construct the possible interactions. So we can go ahead and try to construct it. For example, if you want to talk about possible 3-point amplitude for coupling to a photon, we can do this exercise. For example, if we have spin 1/2, then going back to this rule here, so you see that we have only 1 SL2C indices here because S is 1/2, so you only have alpha 1. And then you also have only beta 1. So you only have 2 indices, alpha 1 and beta 1. So to carry 2 indices, you can either use the epsilon tensor or you can use the lambdas. So that tells you that you have 2 structures here. And these X factors are just there to soak up the correct little group weights. So that's it. That's the only possible interaction that you can write down for a spin 1/2 coupling to a photon. It looks a very clean form. This object, if you take your usual QED amplitude, you sandwich a polarization vector and you do some spinor massaging, and you find that this object X, this is the external line factors, this is exactly this piece. So this is the minimal coupling part of QED, sorry. Now what is G1? Well, then G1 is G-2. Okay, so you see that immediately that because we're defining things from a purely kinematic point of view, these anomalous multiple are no longer, in some sense, they're no longer anomalous in that they're just directly separated in the very beginning. So if you remember from the quantum field theory textbook, you remember that you need to do some gamma matrix manipulation to separate out the G-2 from the minimal coupling. But here it just comes out directly. For spin 1, you can do exactly the same exercise, then you'll see that you have 3 possible tensor structures. So these are the dipole, and this is a quadruple moment. And so in general, for spin S, you're going to have 2S plus 1 possible moments sitting here. Okay. And so since, as I mentioned, that this interaction is just minimal coupling for QED, you can ask for spin 1, what is this coupling? And you'll see that this is actually just the minimal coupling for the weak interaction, WW gamma. However, we can define this for arbitrary spin. So the natural question is to ask, what object corresponds to having in this basis, you have all of these G's, these higher multiples to be 0. What object might correspond to that? In other words, yes?
I have a question in the last slide.
Yes.
If you go back, so like for spin half particle, can one get just from the kinematics also the non-minimal coupling like psi bar, psi, sigma mu nu, f mu kind of term?
Yes, that's this guy.
Okay, but that is non-minimal, right? The coefficient need not be 2, like can be anything. So
yeah, G1
is
can be
arbitrary.
anything. Yeah, G1 can be anything.
Okay, thank you. Okay.
Yeah. Okay, so yeah, so then we would like to ask what.
Can I just ask one more question? Here, these spaces, it doesn't depend on whether you're at a tree level or loop level. It's just completely arbitrary. Is that the point?
Yes, it doesn't depend. So of course, but this is just a feature about 3 points because you're talking about 3 points. So
I see.
the 3-point structure, even at loop level, the only thing that you can have is because there's no invariance. So the only thing you can have is log m squared. So these are just numbers. So you can So we're basically talking about the possible tensor structures. And indeed, so as you know, right, because this will be 0 at tree level for QED, and then at one loop, you get the anomalous moment here. So G1 is not 0 at one loop. So quantum corrections can generate, so for QED, it will generate G1. For electroweak, classically, at tree level, G1 and G2 is 0, but at one loop, you start getting non-zero G1 and G2. Now, actually, yeah, and this is actually an important thing that I'll come back to in the end. But yeah, so far, once we write in this spaces, we immediately see that there's some special couplings, and these are associated with couplings that are just proportional to this X factor. It's just X times these epsilon tensors. So the natural thing. Yes.
Sorry, I have another question. So could this method give us some interaction like Kerr style? I mean, here you give the QED interaction, which is vector-like.
Yes. Yes. So basically, the difference will simply be because here you notice that I'm coupling. So this is describing coupling, right? So the statement is that I'm just writing the tensor structure. I haven't put what the number, proportionality number in front is. So if you have chiral, then what that means is that, so this is the plus coupling to the plus helicity photon. The coefficient for the plus helicity photon will be different from the coefficient for the minus helicity photon, which reflects that there's a parity violation. So there might be a minus sign or something.
Okay, thank you.
Yeah. So this, yeah. All I'm using is just SL2C. So another comment is that because of the fact that this separates at different moments just directly, so it also makes the loop computation from loops. It actually helps in making it more streamlined. Okay, but anyway, so now there's an immediate question: is that this pure X term seems special? Okay, so we know that, for example, if you're coupling a spin S particle coupling to a photon or a spin S particle coupling to a graviton, then there's this special 3-point interaction, which is just X times the epsilon tensor. And here you have X squared because this is a graviton. So you have two powers of helicity. If I put back the polarization tensor, then the amplitude will look like this form. Now, as I already mentioned, spin 1/2, 1, and 2, each corresponds to this kind of coupling corresponds to QED, electroweak, or massive KK graviton, the minimal coupling of these. But the important point here is that this interaction, we can write it down for arbitrary S. So when we were doing this, then the natural thing that we were trying to ask is that, okay, since I can write down the 3-point coupling, but we know that there's no consistent fundamental higher spin particles in flat space beyond spin 2. By fundamental, we mean just elementary isolated higher spin particles. So what could possibly these interactions corresponds to? What are these couplings trying to describe when we're trying to go beyond S equals to 2? Because the point is that you can extrapolate this as to any spin you want, and this is perfectly well defined. So to answer this one, of course, we already know that we have this effective action, this one particle effective action way of parameterizing the possible how possible spinning objects interact with the gravitational field. And so, since they have these Wilson coefficients, what we could, and as I mentioned previously, from these interactions, from these operators, you can get 3-point amplitude. We already have a 3-point amplitude here. Then we can do reverse engineering and see what does this 3-point amplitude look like in this basis. In other words, what are the Wilson coefficients that are associated for this minimal coupling 3-point amplitude? And it turns out, so we did the straightforward matching, and we found that the corresponding Wilson coefficient for S to the N Wilson coefficient, it looks like this for a spin S amplitude. So you immediately see that beyond the leading order is exactly 1, and beyond that, everything is suppressed by S. which means that in the classical spin limit, which by classical spin, we means that since S is really the quantum spin, so we're taking S going to, if we extrapolate S to infinity and taking H bar to be 0 while keeping SH bar fixed, which is the classical spin, then these will all be driven to 0. And we just get exactly the Kerr black hole Wilson coefficient. So in other words, taking the classical spin limit, this higher spin interaction actually seems to be describing the spin multiple for a Kerr black hole. Of course, this is just observations. We can directly do computations to show this. And indeed, if you try to use this minimal coupling, and then we can use, once you have the 3-point amplitude, you can compute the leading this is called the Minkowski expansion, which is just an expansion in G Newton. You can do this. You can get the leading order potential by just considering this process, which you have two objects exchanging a graviton, and since we're taking these far away, so you're taking this transfer momentum q to take the q squared to 0 limit. That in the amplitude language, that corresponds to factorization, and when you factorize, it's just a product of the 3 points. So all you need to do is just take this 3 point and put it in here. So basically the potential is done by this 4-point scattering process, but you take the transverse T exchange to be 0. And then you get the residue of that T pole, which is given by the product of 3 point. And since we are, once again, since we already have the 3 point, you can take the product and then you can do the computation and then Fourier transform back to position space. And this is what you get for the gravitational potential between these two spinning objects. And you'll find that this exactly matches the GR result, that leading order in G, since there's a leading order in G. So this is not just an observation that the Wilson coefficient gives the Kerr black hole in this large spin limit. You also find that if you want to compute physical observables, you can also Kerr black hole classical potential, gravitational potential. And there's also many other things that you can compute. You can compute the scattering angle. You can compute the spin impulse, the impulse as well as the deflection and spin. And so these are really a lot of work that has been done in the past 2 years by also Justin Vines and other collaborators. And right, so there's really a lot of literature now gathering that shows that these minimal couplings actually are reproducing these classical GR computations.
In your previous page, you mentioned you take the limit h bar go to 0. But do you set h bar equal 1 or not in the previous computations?
I say h bar equals 1. Sorry, what did I?
Yeah, you really will take the unit with h bar equal to 1, but how can I see you take h bar go to 0?
I didn't. I haven't taken. So yeah. So of course this needs to be. So you need to right. So you need to put back all the h bar factors, and that comes in. And when you're writing these momentums, now you should not just write momentum. You should write your momentum to be h bar times the wave the wave number. And so it's right. So in taking this limit, what you need to do is you need to put back all the h bar factors in the computation. Yes. And
okay,
so,
thanks.
yeah, so if you take care of that, then yeah, so then this limit is well defined.
Okay, thanks.
Okay.
So here I have a question. So why your result just give you gives rise to the classical GR result? For example, high derivative gravity will come from the loop calculation or something like that.
So do you? So
I mean, suppose I just have a high derivative gravity theory. I can calculate just by this action, and so this will give you classical result, which may not be the same as the classical GR result. So, but in your calculation, your result just gives the classical GR result. So I'm just wondering, high derivative result will come from where
Well, you can have higher derivative, right? So you can have higher derivative corrections by. So once again, so we're reproducing the classical GR result. So for example, you can ask if you have R squared or R cubed, for example, and how would these things affect? And indeed, well, these things will not directly affect this computation. So you won't see those effects here, which is natural because you know that usually when you have R squared and R cubed, they're suppressed by extra factor of n Planck. So, but you will see those effects coming in when you try to compute the next order correction. So if you try to compute, for example, this classical potential at one loop, then those R cube higher derivative operators, they will include in one loop because they'll modify the 3-point graviton vertex. And so your one loop computation of this classical potential will then be corrected.
Okay, got it. Okay, thank you.
Oh, sorry. Can I just ask one more question? It's sort of related. So classical limit doesn't necessarily mean I get black holes. Like what you were saying at the beginning of the talk, I might have things like neutron stars. Is it that I have secretly taken some asymptotically far limit? Or?
Oh no, what has happened is that you use minimal coupling. That's what happened. So if you use something else beyond minimal, so for example, if you started to turn on these extra couplings, then you'll start getting extra.
Okay.
Right. So the statement about like neutron star, if I cast into this language, of course, nobody has really done trying to match neutron star Wilson coefficient into disk spaces. But the way that we will frame it in disk spaces is that when you have things that are other than black holes, then these numbers starts to be no longer zero.
Oh, okay, I see.
So
I see.
Yeah. So the way that you reproduce black hole is just using minimal coupling alone. So this is like further evidence that minimal couplings are describing black holes.
I see. But there's no a priori reason or intuitive reason why this should be the case. Or
yeah, that's exactly the point. And so this is why we were not happy with this. Of course, you can say that. Oh, it's black hole because, you know, since these are continuous number and you know that black hole cannot have any other quantum numbers to characterize it, so the natural numbers associated for these are just zero. You can hand-waving make this kind of argument to argue why black hole just corresponds to this minimal coupling. But that's that's in reality is a cheat. Because this basis, you notice that I only have alphas here, and I'm not having alpha dot. So because you know SL2C, there's alpha and alpha dot. So this is at the chiral basis. So it turns out that it's only the black holes are only simple minimal coupling in the simple form, only for the plus helicity photon or gravity, or if it's electrically charged, then it's photon. If it's not electrically charged, just couples to gravity, then there's gravitons here. And for the negative helicity, it's actually not simple in this basis. So I completely agree with that question. So it seems right now, a priori, there's not a very good answer to why black holes selected these particular interactions. And that was actually one of the reasons that motivated us to look elsewhere. For what how are these couplings special? But before I move on, I would like to just present you that. So after the analysis, of course, there's many work done by other people, and right now we now have a complete classification of all the possible 4-dimension black hole-like solution in terms of these minimal couplings. So let me just briefly mention. So here, given by these minimal coupling, what I mean is that you use these minimal couplings and you compute these scattering events, extract the gravitational potential. At leading order, these give you exactly the gravitational potential for these, or observables for these black hole-like solutions. So for example, if it's just Schwarzschild, then it's just basically the original minimal coupling with no spin, because the Schwarzschild doesn't have spin, and it's just the simple minimal coupling. If it's Reisner-Nordstrom, then that means that it has a minimal coupling to graviton as well, with the companion minimal coupling to a photon. For Kerr, which is what I just mentioned, what you have is you have these higher spin, arbitrary higher spin result that minimally couples to the graviton. Kerr-Newman is these higher spin result coupled to graviton, as well as higher spin result minimally coupled to a photon. You can also do top-knot, and what the top-knot solution corresponds to is again minimal coupling, but then it has a phase rotation, which is much like, so there's also an interesting story here about what electromagnetic duality means in here, because this is really electromagnetic duality. And in a more recent paper that should come out soon is that, of course, you can generalize this to Kerr top-knots, and you can show that it is basically, once again, minimal coupling for arbitrary spin with an extra phase rotation. So, and this essentially completely classifies all the possible minimal coupling that you can possibly write down. And each one of them that you write down, each combination gives you a distinct known black hole-like solutions in 4 dimensions. Okay, good. So I think I'm running a little bit behind on time. So let me just go to the crux of the question. So let me just skip a few slides. So we'd like to ask, what is this minimal coupling is telling us about Kerr? So, or in other words, is there some a priori physical principle that selects these couplings? Now, these couplings are actually special in some sense. So for example, if you take these coupling and you take to the high energy limit, then these couplings match to the usual notion of minimal coupling for the masses theory. So for example, I already mentioned QED, you can match to F squared for vectors. You can, sorry, there's a psi missing here. So you can match to the gravitational, the Rarita-Schwinger interaction for spin 3/2, and you can match to gravity, high energy limit. So these coupling directly matches to these minimal couplings that we know in the high energy limit. However, as I mentioned, for S equals to beyond 2, which is really what's giving the these multiples, all of these multiples of black hole, there are no such interpretation because there are no massless higher spin in flat space and higher and beyond spin 2. So we don't. So this kind of story doesn't really work for going beyond S equals to 2. Now, as I mentioned, you can also say that it's because that's the only thing you need to write down, and you don't need all the other G factors there. But like I said previously, that this is just a cheat because I was writing it in the chiral basis. If I choose instead to write it in the anti-chiral basis, it will not be simpler, and it will not be simplest. So we would like to, so this is the thing that was, so it was very nice that this is helping us. It's also giving us very efficient ways of computing these gravitational observables that for the past 2 years. But this was something that was nagging us, that we don't know what physically chooses these couplings. And so then we started to think about entanglement. So of course, it's completely natural to think about entanglement from an S matrix, because the S matrix is basically the matrix element, a transfer from in state to an out state. So if you have some 2-to-2 scattering, then you have some in state A and B in state, then you get an out state, then you can obviously try to compute how the entanglement, if the A and B have some entanglement or have zero entanglement, how does the entanglement change between the in state and out state? So we can do exactly the usual thing. You can take the out state, construct a density matrix, trace out particle B, and to get a reduced density matrix. And then we can ask about the, I know that there, I think, yeah, we can ask about the increase or the decrease in entanglement entropy between the in state and out state. And so we can ask about this quantity. Of course, this is a very natural thing to do, so it must have been done a long time ago, and precisely because it's been done a long time that we know that there's particular obstructions in trying to do this for usual scattering events. And that is that when we're talking about phase space, for example, if you want to trace out the phase space, what exactly is this phase space? Now, since this is in flat space, if you talk, usually before people try to talk about spinless particle, entanglement of spinless particle, then you need to trace over the momentum space. But the problem then becomes that since you're tracing over momentum space, we're talking about this flat space scattering, then you encounter the fact that the divergence have infinite volume, and there's various issues about regularization, which then makes the, I'm not sure if there's a defined regularization independent object that people have identified where it's reasonable to talk about the entanglement. So, but this is a well-known problem that has been discussed in various papers. So I recommend this paper, which actually gives a very good exposition of this issue. The other thing is that we can think about, instead of tracing, think of these as Hilbert space of momentum space, I can think about if they carry spin, I can think about them as states in the spin state Hilbert space. Now then there's also a problem because the spin state Hilbert space here of the incoming particle and the spin Hilbert space of the outgoing particle is distinct. And it's very simple because the spin state is the spin space is basically defined by the little group space. And the little group is defined with respect to a momentum. And since the ingoing and outgoing momentum are different, their little group space are completely distinct. So when you can talk about the entanglement of these two particles in the spin space, and if you want to talk about the change of entanglement or the increase or decrease of entanglement, we're basically comparing apples to oranges because the space of the outgoing and the space of ingoing are basically not in the same Hilbert space. Now, however, this second issue has already been treated in these recent works that have been trying to derive the potential or the conservative Hamiltonian from the S matrix. So from the experience that I have gathered for the past 2 or 3 years, we actually know how to deal with this issue about this distinct Hilbert space. So let me just go back a little bit and talk about what happened with this little detail that I skipped over when I talk about going from this effective one particle Lagrangian to scattering amplitude. So remember that when we talk about this and we talk about scattering amplitudes, we take this as operator. They were initially well-defined operators, and then we sandwich it between polarization vectors, and voila, we get the amplitude. And therefore, when you talk about the amplitude, then the amplitude becomes some coefficient, then depends, of course, on these Wilson coefficients. And I'm just going to define this W tau here, which I'm going to use later on. Good. Now, once we have this, so when computing the potential, then we basically just take this 3-point interaction and then put it on these two sides. And these corresponds to the residue of this Q exchange, taking Q squared equals the 0 limit, which is a long distance limit. And so basically the potential is identified from this form. And you notice that there's an extra, which is previous I didn't mention, but you actually need these two extra factors here. And this is what we call Hilbert space matching factors, or what is also known as the Thomas-Wigner rotation. So what this object here that we construct what this object does is to match the Hilbert space of the outgoing state back to the Hilbert space of the incoming state. And so the way that this is done is, so for example, you can think about it as following. So you set up, so let's say you have a reference frame. So we have some reference space for some reference momentum. So you can set up the polarization. So here I'm just going to use polarization vector. You can do the same for polarization tensor and other higher rank spins. So you have so in the reference momentum frame, your polarization vector, because it's transverse, it's just a delta function with a spatial component. For any momentum, then, it's just related to this reference momentum P naught by a Lorentz transformation, which tells you that the polarization vector is also related by this reference frame polarization vector by a Lorentz rotation. So that means that you can immediately relate the outgoing polarization vector back into the incoming polarization vector by a succession of Lorentz transformations. And the Lorentz transformation are basically defined by the momentum, outgoing momentum, ingoing momentum with respect to whatever a reference momentum that you choose to use. Now, why is this important? It's because that, remember, in quantum field theory, when we introduce these polarization vectors, the role of these polarization vectors are precisely to carry the little group indices, or they're precisely the frame that spans the little group space. So this equation tells you that I can take this frame of the outgoing spin space frame, and I can translate back into the in space frame. So for example, if you have some interaction that relates some in space frame to an out space frame, then you know that you can translate everything back into the in space frame. So they're all in the same little group frame through this extra Lorentz rotation factor. And then this Lorentz rotation factor precisely contains what is known as this Thomas-Wigner rotation. So it's not entirely true that you just need a 3-point amplitude. You also need this Thomas-Wigner rotation factors and get translating everything back into the same Hilbert space. So we've already learned how to do this and trying to compute these gravitational potential. And indeed, so you can work out explicitly what these rotation factors are. I'm just giving it here. So these are just the velocity, the proper velocity of these particles, and A is the spin. And you can take this and you can augment it here. And once again, these W's are for arbitrary Wilson coefficients. And to make sure that we're doing the correct thing, you can just expand out and compare the potential that you get here by what is computed in all these literature that is done before, which use traditional GR methods to compute it, and you can find that these give exactly the correct answer. So this is just some from reference of things that has been matched, and of course because we have this, so we can compute the arbitrary spin. So we actually have predictions for beyond these what has been computed before. Okay, but this is of course this is not the point. The point here is that we know how to do this Thomas-Wigner rotation to map the Hilbert space back. So in other words, this is not a problem. We can talk about spin space entanglement because this issue about distinct Hilbert space, we know how to deal with it. So right, good. So we're ready to go. So we consider the spin Hilbert space of particle A and particle B. And once we have an incoming state, we know that the S matrix, the 2 to 2 S matrix will map out to outgoing space. The only new thing that we need to do is we need to augment it by this Thomas-Wigner rotation factor so that the outgoing space is described in the same Hilbert space as the incoming state. So, right, so then we do exactly the same thing. We do the constructed density matrix, take the reduced density matrix, and then we compute the Van Neumann entropy. And then we can compare the Van Neumann entropy between the outgoing state and the ingoing state. Of course, you might say that this depends on what the incoming state is, as we will show that actually it doesn't depend. But you can also define what is known as the entanglement power, which is a way of entanglement, which is independent of the incoming state, because for this object you need to integrate over the incoming state phase space. So this is our plan. We're going to compute either the Van Neumann entropy or the entanglement power, and then we're going to compute this 2-by-2 scattering. But we don't want to just compute at this order. So what we want to do is we want to resum the entire ladder diagrams. And this indeed is what is well known as the Eikonal limit. And the way that you compute the Eikonal limit is that you take the leading order G amplitude, you do a Fourier transform, and then you exponentiate it to get your Eikonal limit S matrix. So yeah, so basically that's what we're going to do. We're going to take our tree level amplitude, which we just compute, which means that it's leading G, and we're going to compute it for arbitrary Wilson coefficients here. And then we're going to scan over that Wilson coefficient and see how these entanglement changes as we scan through these Wilson coefficients. And so I think I'm almost already in 1 hour. So I mean, but these are just details. So you can see that, so basically this is the computation that you need to do. You take the tree level amplitude as a product of 2 3 points. These W's here encode the Wilson coefficient factors here. The theta are basically the rapidity. So these are just kinematic factors here. These S are the spin operators. They're usually defined as the spin vector, which is the Pauli-Lebensky spin vector. And you want to translate that back into spin operators acting in the little group space, which is the straightforward thing to do. You can just do it translating it back into this bold S. And the bold, in terms of component, you can see that it takes this form where sigma is the usual spin operator, or the spin matrix that people are familiar with. So we do this translation, and then we get this form, and of course the M bar tree, which you need to do to put, which you need to use to put in here to get the Eikonal phase, and you need to tag on the the Wigner rotation to get to such that the Eikonal phases you're talking about transitions within the same Hilbert space. Okay, and so you can do that, and so this is the form that you'll get for your tree amplitude. So these are just a bunch of operators that acts on the spin space. And these A's are coefficients. And these coefficients, if I write it out, so for example, I only wrote out to a spin 2. So these coefficients will now depend on non-trivial Wilson coefficients here. So we have the M bar, then it's just straightforward. You do a Fourier transform to get the Eikonal phase, and then you plug it to get the Eikonal S matrix. And then we can start looking at the entanglement. So once you have we compute the Van Neumann entropy. So here there's a plot. So let's start with spin 1. So spin 1, you're parameterized by this, where you have 2 Wilson coefficients. Once again, when C equals to 1, that corresponds to the black hole value or the minimal coupling. And so this is the change. And so this is the change. These 2 graphs looks almost identical. So, but this is computing different things. This is computing the change in entropy from the incoming state to the outgoing state. The way that you can compute it is 2 ways. First, you can, of course, the incoming state, you can throw in a pure state. So whatever Van Neumann entropy you get from the out state is the difference. Or you can put in some entangled state already in the in state, and you get the out state entangled, and then you compute the entanglement entropy, and you take the difference. The plot is identical. And so basically, you see that in the minimal here, the minimum is exactly, so it's not so clear, but it's actually exactly C equals to 1, 1. And you see that, so this is a black hole value is the minimum. And at the minimum, the change in entropy is extremely small. So this is 10 to the minus 9. You can compute, instead of the change in entanglement, you can compute the change, the entanglement power instead, which is an in-state independent thing. And once again, you get almost the identical plot, and you get, once again, the black hole at minimum entanglement. These are the parameters that we've used to make this plot. So this is just including spin operators up to degree 2 spin operators. Once again, black hole, when you talk about these spinning objects, you have infinite number of spin operators, include 1 by 1. So the next thing we did was we went to spin 2, which now have 3 Wilson coefficients. So spin 2 means that we're going to degree 4. So we have 3 Wilson coefficients now, and you can tune each Wilson coefficient once at a time. And so these are the plots for once again, the change in entanglement. And so this is the first sheet is if I'm tuning the S square Wilson coefficients, this is S cubed and S to the 4th. And once again, so even though these are slightly rising, but inevitably they're all heading near 0 at the black hole value. You can play a lot more. We also went to spin 3, which now has 5 Wilson coefficients. And as you see that as you increase the spin, the change in the entropy rapidly rises away from the black hole value. So now you can see that you have a steep valley here. So this is the plot of C2, which is again S2 operators. And yeah, I mean, you see that this is a steep valley where you have the central here, which is a black hole value, which is still very small. So this is keeping all the other 4 Wilson coefficient fixed and just playing with C2. This is what we did with just playing with keeping C2 and C3, all other 3 Wilson coefficient fixed, but C2 and C3 being arbitrary, and then we plot this. And once again, you see that the black hole value is near the bottom. And one of the things we observe is that it seems that C2, the S2 operator, even though each operator, once it deviates from the black hole value, it starts to increase the entropy. But it seems like the S2 value, the S2 operator has the most dominant effect. And so this is another, you showed, and as you increase the spin of the spin state, the increase of the spin 2 operator that generates entanglement increases more and more faster. We've done multiple scans, so yeah, so this is just basically scanning through all possible combinations of Wilson coefficients. So so there's a total of 9 possible combinations you can deform, and each and every case this is robust. Once the moment that we move the Wilson coefficients away from black hole, the entanglement just increases, and the black hole value is always at the minimum. And it's also very non-trivial because this is not like some coefficients which is 0, which has a special point at 0. This minimum is at the point when the coefficients are 1. And so, yeah, so if we didn't know about how these coefficients came from, if we didn't know about that 1 came from the fact that it is minimal coupling, if we didn't know that, we wouldn't have I mean, if we just see that it's very mysterious why that 1 is always at the minimum, it will be mysterious. You would think that it should be 0 is at the minimum, or 0 should be the special point. But no, actually it's 1 that's at the special point. Right. So this is basically the main the main point of our paper, which it seems like we found the underlying principle that select these minimal coupling, and that is that when you consider the S matrix that it generates, it seems like the minimal coupling is at the S matrix in which it gives 0 entanglement generation. So usually when you think about an S matrix, it couples. You think about 2 particles. Especially in these ladder diagrams, it's exchanging multiple massless particle between them. You'll think that the outgoing state must be much more entangled compared to incoming state. But somehow when you have these coupling given by these black hole couplings, this multiple exchange, even though it's going a ladder diagram, it's giving you multiple exchanges, the outgoing state is giving you exactly the same whatever entanglement value you had in the in state. It gives you back in the out state. Okay, so this is the end of my talk. So of course, there's many things that we want to look at. So in this talk, we've seen that in terms of this on-shell basis, many of the black hole solutions, properties of the black hole solutions are cleanly captured. In particular, just that simple minimal coupling generates the entire black hole multiple expansion. And it appears that we haven't identified maybe part of the principle, that the principle behind what is special about this minimal coupling, and it appears that it is generated spin entanglement. So the point about near 0, of course, we're doing Eikonal approximation. So that might be interesting that whether it's actually strictly 0 or it's near 0, since we're doing Eikonal approximation. So we don't know if actually if we become more and more accurate, whether or not this really continues to even continue to shrink to 0. Now, of course, there's a lot of things to do. What is the story beyond leading order in G? So what happens when G squared come in? And of course, the most interesting things which we're also looking at now, which is the quantum corrections. So actually, so if we start with minimal coupling, or what sort of couplings generically, does these multiple moments, which are 0, now start to come back in? So do we have these anomalous multiple moments? Of course, we can do we can do the same. And so this is just Kerr black hole. You can start thinking about charged black hole, SUSY black hole. What's the difference between what happens is something special happens when you hit BPS states, BPS configurations. What about top-knot solutions? And also there's parallel discussion recently about other directions towards these multiple moments. And there's these very concurrent paper, interesting concurrent paper, where, for example, they instead of talking about the multiple moments for us about these Kerr black holes, they talk about the black hole microstates, and in particular how to distinguish between these multiple moments coming from a Kerr and the multiple moments, for example, coming from the fuzzballs. And yes, so it'll be also interesting to see, since now we've established that you can take these multiple moments, construct scattering events, and then look at the out states spin configuration with the in states. Yeah, these are also interesting to look at what are special with these configurations. Okay, so I guess that's the end of my talk. Thank you for the attention.
Thank you very much. Questions?
Sorry, I have a question. I'm wondering if you consider the scattering amplitudes for two naked singularities, For example, the Schwarzschild solution with minus mass, would you still get the minimal coupling behavior or something else?
Minus mass.
Yeah, I mean naked singularity.
Oh, you mean, yeah, because we are really far away. So, right, I mean, maybe this is also related. For example, do we see that, so what happens when the black hole becomes, so from the Kerr black hole becomes extremal? If it goes, if it goes beyond extremal limit, for example. So these we can, so these are not, because we're doing these multiple expansions. So we're, first of all, we're far away, and so that we can do these analysis, and so that we can do these Eikonal approximation. And for example, if you talk about extremal black holes, we can't really talk about it in this context, because as you know, that you see that we're basically, in the very beginning, you're doing an expansion in A. So you're assuming that A is not large. So you're having a series, so you're basically, and we're not in the large spin limit. So this entire, so then you can talk about, so in other words, once the spin is large, you cannot talk about the multiple moments one at a time, because there's an infinite series, and the series is non-convergent when you're talking about near. And so these horizon issues, these extremal horizon issues about naked singularities, these are, at least at the current stage, we're not able to discuss it, apply to those contexts.
I see, thank you.
Any other questions?
I have a question. So when you are talking about macroscopic objects like black holes or neutron stars, what do we mean by having these particles gaining entanglement entropy after scattering?
That's a good, because you're talking about their states, their spin states they're continuous in their classical spins. In that sense, I'm usually I'm a little bit abusing my language here. So really what I'm trying to say is that here what we're doing is we're talking about minimal coupling for arbitrary arbitrary spin. So there's two connections. First of all, we have the minimal coupling for arbitrary spin. For this, you can compute the entanglement no problem. And at the same time, we know that this minimal coupling for arbitrary spin, if you take the classical spin limit, you go to black hole. So it's not the direct relation between the entanglement we compute here, because we're still computing order by order in spin, and directly related to the black hole, which is the infinite spin limit in principle. So it's not really a direct relation. But I'm a little bit using abusive language in that minimal coupling gives black hole, because that's the only thing. Because once again, there's no higher spin objects that it can match to. So you take the high spin limit, you match to black hole. At the same time, the nice physical property about it is that it generates zero entanglement. So that's basically the statement I want to make.
Okay, thank you.
Hi, Yutin. I have a question. So, can you formulate these things for wormhole?
That would be going to Euclidean. Yeah, that's also an interesting thing that we're thinking about, because there's one thing that is also being swept under the rug is if we really deal with this if we really deal with if we really talk about the 3-point amplitude here, because everything is based on this minimal coupling 3-point amplitude, and we know that minimal coupling 3-point. If you want to talk about it, you have two choices. You can either you need to either complexify it, or you need to go to 2-2 signature, and so you can so this is one of the things that we want to really understand, is that what is the difference between going to complexification and going to 2-2 signature, because one of the for example, the wormhole scenario. So it's going to one choice compared to the other corresponds to that the geometry that you're discussing is going from, instead of the usual geometry to going to the wormhole, you do the Euclidean version, and you go to the wormhole configuration. That is, I'm not directly involved in that. I think Donald is thinking about that, is really thinking about these different signatures. What does that mean for this 3-point coupling? But I would imagine that there might be some connections related to the fact that there's actually different choices of analytic continuation, because you need to do analytic continuation when you're talking about the 3-point amplitude. Yeah, but that's basically what I can say. Yeah.
Another question is the SH bar can be considered as the physics spin of the perhaps?
Yeah, so SH bar is the classical spin.
It's the spin of the black hole.
Yeah.
Okay.
Any other questions? So if not, let's thank the speaker again.
Okay. Thanks, everyone.
Thank you very much. I will stop the recording.